Hello everyone, we are at the topic of transistor amplifiers, and today we're going to study the biasing methods that are commonly employed in discrete transistor amplifiers. So if you remember previously, we saw that to be able to use MOSFET or BJT transistors as a linear amplifier, we need to make sure that they operate in the active region. If you look at the transfer function of these two transistors, you can see that their transfer function is approximately linear when these transistors operate in the active region, which is here, this region, and this region for the case of BJT. So DC bias point for these transistors are the DC current and node voltage values for the transistors. For example, for the case of MOSFET, DC bias point, by DC bias point we mean the DC drain current and DC drain to source voltage, and for the case of BJT, the DC bias point consists of the DC collector current and base current and emitter current and the DC collector to emitter voltage. So a stable and robust bias point should be predictable and insensitive to variations in temperature and to the manufacturing variability in the transistor parameter values, such as Vt, mu n, C aux, W over L, and beta for the case of BJT. And bias point details impact the small signal response, like gain of this voltage gain of the amplifier. So an essential step in the design of a transistor amplifier is the establishment of an appropriate DC operating point for the transistor. This is called biasing or bias design. The simplest bias circuit is when a fixed voltage is applied to the base of BJT, for example, through a resistive voltage divider circuit, or with a resistor which is connected to a DC voltage source. So these two circuits, in terms of circuit analysis, are equivalent because you can reduce this circuit on the left to the one in the right. So I can do that by drawing the Thevenin equivalent circuit of the first one. So if you look at this one, I can find the Thevenin equivalent circuit of this resistive voltage divider network, and it's going to be the same as this one. Let's take a look at this one. Let me label this one node A. I'm labeling this node A, and this node B. And if you do that, I can draw it like this. So this is my node A. There is R base 2 connected to it, and there is another resistor R base 1 connected also to node A, this one, and there is a voltage source VBB connected to here. This is VBB, and this is my node, the second node base. Now I can find the Thevenin equivalent circuit between node A and node B, and if you do so, you're going to have a resistor here. I'm going to say this is the Thevenin equivalent resistor. I'm going to show it with R sub B, and this is the Thevenin equivalent voltage, and then I'm going to show that VBB prime, and this is node A, the same node A and node B, and this is grounded, so it's going to be exactly the same thing as this one in here. So for example, they are the same A and B nodes, A and B. Okay, so these two circuits are, in terms of circuit analysis, equivalent, and the equations that I provided here are for this circuit here. Let's look at the equation, the KVL equations that I wrote for this circuit in here. So from base emitter KVL, I can write that V sub BB is equal to I base multiplied by R base plus a base emitter voltage. From there, I can calculate a base current, which is base VBB minus base emitter voltage divided by RB. Because this transistor operates in the active region, which is my desired operating region because I want to use it as an amplifier. I know that I collector is equal to beta times I base. From there, collector current is equal to this equation. And from the collector emitter KVL, I have VCC is equal to ICRC plus collector to emitter voltage. In this transistor circuit, if the value of beta changes, the value of IC, the collector current, is going to also change, and from there the value of VCE is going to change, because in this equation, if IC changes, the value of VCE is going to change. Now, if I want my transistor to operate in the active region, the DC collector emitter voltage must be greater than VD node. However, if IC changes and VCE changes, it might happen that collector emitter voltage would be below VD node, and then my transistor would go to the saturation region. So But this biasing circuit drastically depend on the value of beta, and because of the changes on the beta value, which is common in the discrete transistors, it's not a good biasing circuit. So changes in the BJT beta or BBE value changes the bias point drastically. BJT can end up in saturation or cut off easily. And I want to have IC greater than 0 and VCE greater than VD node for the transistor to operate in the active region. A better biasing circuit is a biasing with emitter degeneration, and it is when you add a resistor to the emitter resistor to the previous circuit. So doing so has the benefit of eliminating the effect of changing beta to the bias point of this transistor, or at least reducing it. Let's take a look at how this works. So let me write the base emitter KVL here, and that's going to give me VBB equals to R base multiplied by I base plus base emitter voltage plus RE multiplied by IE, and from there VBB minus base emitter voltage is equal to IE multiplied by R base divided by beta plus 1 plus RE. Now in this equation, if R base divided by beta, this one, is much smaller than RE, then I can neglect the first term. So if R base divided by beta plus 1 is much smaller than RE, then VBB minus base emitter voltage is almost equal to IE multiplied by RE. So I remove the beta dependent term in my equation. Now this IE, which is almost equal to IC in the active region, is independent of the value of beta. So emitter resistor provides negative feedback in our circuit in this configuration, because I can write the base emitter KVL like this, assuming that R base multiplied by I base is small, or base resistor divided by beta plus 1 is much smaller than emitter resistor. And I know that collector current is proportional to e to the base emitter voltage divided by terminal voltage. So in this circuit, if collector current increases, for example, because beta increases, then the value of VBE is going to decrease because IE is increasing, RE is fixed, base emit and VBB is fixed. So if emitter current increases, base emitter voltage is going to decrease, and because this one decreases, I collector is going to, or I emitter is going to decrease. On the other hand, if collector current or emitter current decreases because of changes in beta, and when beta decreases, then base emitter voltage is going to increase, and because IC is dependent on the base emitter voltage in an exponential format, IC is going to increase. So the emitter resistance provides negative feedback and provides stability in our circuit. So the basic arrangement for emitter degeneration bias circuit is on this one, and we had this base emitter equation, a KVL equation before, and you can build that circuit by using a resistive voltage divider network, as you can see here. And if you do so, base MVBB in this equation, VBB is equal to R2 divided by R1 plus R2 multiplied by VCC. So, and RB is equal to R1 in parallel with R2. These are the parameters in this KVL equation. So we already saw how to find the Thevenin equivalent of this voltage divider circuit. Let me expand this one, so this include this VCC. Now the middle circuit, this one can be built using one power supply. The other configuration is using two power supply, which is this one in here, and I can write the KVL in this base emitter loop, and if you do so, I base multiplied by R base plus base emitter voltage plus RE multiplied by IE minus VEE is going to be equal to 0, which is the same equation that you have in here. MOSFET biasing circuits are similar to the ones that we had for BJTs. And the first one and the simplest one is the fixed bias bias circuit. The easiest one and the first and the easiest one is the fixed bias method for the MOSFETs, and that's when you apply a fixed voltage source to the gate of this MOSFET. You can do that by adding a resistive voltage divider network to the gate. For example, this is RG2, that is the same as VDD. You have your MOSFET RD connected to VDD, and this is the source connected to the ground. So the voltage at this gate node is going to be equal to VG. So ID equation, we know the ID equation for the case of MOSFET operating in the saturation region, and this is the second one is the drain to source KVL equation. So this method is not desirable because the value of VT, W over L, mu n, and Cox vary widely among devices even from the same manufacturing part number. So if any of these parameters changes, the value of ID is going to change, and if ID changes, the value of VDS is going to change. So as a result, bias point or ID and VDS can change drastically due to the temperature or manufacturing variability, and it's not desired for using a transistor as an amplifier. What you can do, biasing with source degeneration is the solution for the previous problem, and that is when you add a source resistor to the source of your MOSFET transistor. In that case, the gate to source KVL is going to be VGS is equal to gate voltage minus RD multiplied by RS, and again you have the ID equation for the transistor operating in the saturation region. Now if ID increases, for example VT decreases, or one of the parameters mu and Cox W over L increases, then from the gate to source KVL, if this one increases, VGS is going to decrease, and if VGS decreases in this drain current equation, ID is going to decrease and it's going to be stable. And for the case of ID decreasing, for example when VT increases or one of those parameters decreases, then gate to source voltage is going to increase, and that's going to increase the ID value. So you're going to get a stable bias point by adding a resistor to the source of this transistor. So similar to the BJT case, we have for the source degeneration bias circuit, this is the basic arrangement, and you can do the same circuit by adding a voltage divider network to the gate. You have this emitter at the source resistor to generate the source degeneration bias circuit, and in this configuration you can use only one power supply. You're using one power supply to build a circuit, and the gate voltage is equal to VGS plus RD times RS. And or you can use two bias power supplies, this negative VSS and VDD, and the gate to source KVL is because IG is equal to 0, you can write 0 equals to VGS plus RID multiplied by RS minus VSS, which is the same equation as you have in here.